I built my first simulation model in the year 2000. My early work taught me that managing your experiments was key to running a successful simulation study. So in this video, I'm going to show you how to set up reproducible simulation experiments. You'll learn how to conduct multiple replications of an experiment and how you can batch multiple experiments up and run them all in one go. It's a big video and I'm going to throw in two bonuses. The first is that we're going to learn how to implement common random numbers in our simulation. And second, we're going to learn how we can store our simulation experiments in a file, read them in, and run them in a batch. So here's our design. The most important change we're going to make is we're going to create an experiment class. That's going to provide a place where we can store input parameters for our simulation model. It's going to contain default values, and it's going to allow us to change those values so that we can observe the impact on the simulation model's outputs. Secondly, it's going to provide a place for us to collect results as an experiment runs. This is a change from before where we had a notebook level variable, in effect a global variable. We're going to scrap that and store our simulation results as member variables as the simulation runs. And lastly, it allows us to control pseudo-random numbers. We'll be able to finely tune what random numbers are used from an experiment. We're going to create instances of experiments. So for example, we could have a default experiment where we run the simulation using all default values that we've set. Or for example, we might run a busy day simulation where the mean inter-arrival time is reduced and we observe what's the impact on waiting times and utilization of that effect. When we've got an instance of an experiment, we're going to pass that to a new function called multiple replications. That is going to make use of our single run function. It's going to call that multiple times depending on what value we've set. We're going to pass the experiment, in this case a busy day, to that single run function. And that's going to pass the experiment to our SimPy process model, where experiment is now a parameter. So all our hard-coded parameters that we had within the simulation model have now been removed and they're stored within the experiment class. Each time a single run completes, the results will be returned to the multiple replications function. And what it will do is it will construct a replications table. So for each replication, we'll have a waiting time result and a utilization result. So we'll have a nice clean table of results at the end of the run. The other thing you'll notice about the single run function is that we pass in a replication number. That's a simple integer value which represents a count from 0 or 1 to the number of replications we're going to obtain. And we're going to use that number as a seed for the pseudo-random number generators within an experiment. That allows us to get a really nice repeatable model that gives us the same results each time we run it. That's going to reduce the headache of debugging our model. The other nice thing about this design is because we're using instances of experiments, you can envisage a scenario where we create big batches of experiments that we might run in one go. We could hard code those experiments within a function, but the other nice thing we could do is store those within a file, for example, a comma separated value file, and have a function that creates this batch of experiments in one go. All of the code we're going to go through in this video is available in an interactive Jupyter notebook. You'll find the link to that in the description below. Let's define some defaults for our experiment class. So these are defined as constant variables here. We have the number of operators, we have our inter-arrival distribution parameters, we have our call time parameters. We have some general sampling settings. So we require two streams of pseudo-random numbers, one for the inter-arrival times and one for the call duration times. And our master seed, if you like, our default random number set is 0. And we'll cover what that means in more detail when we get to common random numbers later on in the video. We have a Boolean flag here to switch off tracing or logging simulation events if we wanted to run the model in debug mode or if we wanted to run the model in experimentation mode. And we have a results collection period or run length of the model here of 1,000 time units, in this case, minutes. So to clean up our code, I've defined two distribution classes here for the triangular and exponential distribution I'm going to link at the top to the random sampling video in case you need a refresher. But essentially, a distribution class packages up a numpy random number generator object, the parameters for a distribution, and a random seed. And it's entirely for convenience and also modularity of our simulation. So if we take a brief look at the triangular distribution, we can see here we pass in the parameters of the triangular distribution and a random seed. The initializer creates a random number generator, stores the parameters, and then we have a sample method. And each time we call that, we sample from the triangular distribution. And now if we've set a seed, we will get repeatable results from that sampling method. The experiment class is the most important thing we're going to learn about in this video. An experiment encapsulates the parameters that the model requires in order to run. Those parameters are going to have default values, but we'll be able to easily vary those parameters to explore how this affects the simulation model. In fact, what will also happen is we'll store the results of that run of the simulation within this experiment itself. And finally, an experiment provides us a way to control and set the streams of pseudo-random numbers that the statistical distributions use within our simulation model. So all of this is defined within the class called experiment here. We have an initializer that accepts the list of parameters required by the simulation model. So we have the number of operators, the mean inter-arrival time, parameters for call duration. We also have some sampling parameters. So we have the random number set. So you can think of that as the main random seed that we're going to use for a replication of the model. When we vary that number, we get different results. If we keep that number the same, we'll get the same results. We also have the number of streams. That represents how many pseudo-random number streams we want to spawn for that random number set. This is going to allow us to implement common random numbers across the model. You can see that for each of these parameters, we're passing in default values that we defined above. So if we wanted to, we could just create an instance of experiment and we'd run a base case or default simulation experiment. Setting it up in this way also allows us to easily implement batch experimentation that we'll explore later in the video. So the initializer method is pretty straightforward. We're storing the parameters passed in member attributes of the class. We also create a dummy variable here called operators. That's really a placeholder for the SimPy resource that we're going to create later on. We can't do that now because we need to create the SimPy environment before we do that. This will make more sense when we look at the modified single run function. We initialize our results collection. This effectively means create a new dictionary with empty results, and we initialize our sampling. Now there are three key methods implemented within the experiment class. The first is set the random number set. So this is setting the top level seed that's going to be used for each replication of the model. And so each time we run a new replication of the model, we'll change the random number set that we're going to use so we get different sampled results. So the way we'll implement this later on is we'll pass in the replication number that we're using. This is a really neat way to set up your model because it will allow you, for example, to say, I want to look specifically at the results from replication 3 of my model, and I will always be able to obtain those results by setting the random number set. So we store that value and then we recall the initializing sampling method in order to spawn new random number streams and set up the distributions for inter-arrival time and call triage. So that's what we're doing here in initialize sampling. The first thing we do is create a seed sequence object, and we've passed in the top level seed, the random number set. And then from that, we spawn n streams and we store those seeds within a variable called self.seeds. That's just a Python list. So then when we create our statistical distributions, the exponential and the triangular, we pass in our parameters, but we also pass in the respective seeds. So for the exponential distribution, we're going to use element 0, and for the triangular distribution, we're going to use element 1. I'll link at the top back to the random sampling video for you to get a refresher of how that works if you need it. And then finally, we have a method for initializing the results variables. All this is doing is creating a new results dictionary. This was previously a notebook level variable. We set up an empty list for the waiting times of calls, and we set up a total call duration, a running total that is of 0, that will vary as the simulation model runs. So let's have a look at what it means to use an experiment. The first thing we'll do is we'll set up a default experiment. So the syntax is really straightforward. We simply call the experiment, create an instance of the experiment class. We've called that here default experiment. And if, for example, we wanted to sample from the arrival distribution, we would use the dot notation, access the arrival distribution that we've created, and call the sample method. And we can run that and get different results. Now that is reproducible. So if we recreate that, we will get the same values. Here is the number of operators that we also saw, but we could also look at, for example, the mean IAT. Okay, so that's how you create a default experiment. If you wanted to create a custom experiment, you would simply pass a value to the optional parameter of when you're creating an instance. So for example, if we wanted an extra server, we would just set the number of operators parameter to 14 instead of 13, and then we'd have an experiment with an extra server. So it's a simple object that encapsulates all of the parameters, the results, and the random sampling for each experiment. So now let's take a look at how we would modify the model code. First function we'll change is service. We're going to include an instance of the experiment class as a mandatory parameter to service. And now remember, that instance contains all of our input variables. It contains our statistical distributions. It contains our results that we're going to store within the simulation run. So now when we want to request a call operator, we are using the instance of the experiment and how many operators are available within that experiment that we request. When we want to store results, for example, the waiting times, the list of results for waiting times is stored within the instance of experiments. So again, we use the instance of experiments and the dot notation to access the results dictionary. If we want to sample from a distribution, we've now uncoupled the type of that distribution from the simulation logic. So we use the instance of the experiment and then we access the call distribution object. We don't need to know what type of distribution that is in order to get this to run, because we just know that that is guaranteed to implement the sample method. That returns our call duration, and we then yield that timeout as we would have done before. The modification to the arrivals generator is pretty similar. So we're going to have a mandatory parameter representing an instance of the experiment class. The first change we're going to make is that the inter-arrival distribution is now a variable, an object within the instance of experiment. And again, we just call the sample method here to return the inter-arrival time. So again, we've uncoupled that type of variable from the actual simulation logic. We can now vary that as we please and our simulation will still run. And then when we create an instance of the service process for SimPy, we've got to make sure that we remember to pass in that instance of an experiment, because it's now a mandatory parameter of that function. The single run function is also modified. We're going to include an instance of experiment as a mandatory parameter, and we're going to include a new optional parameter which represents the replication number. And if you omit that and just call single run, it will always run replication 0. So the first change to the code is that we initialize the results variable for an experiment. We set everything back to 0 at the start of a run. And then we initialize, or we set the random number set, and we pass in the replication number. So this is a cool bit of functionality that actually implements common random numbers across our experiments. So each time you run replication 1 of an experiment, it will use random number set 1. Each time you run replication 2, it will use random number set 2. That's going to enable us to have both repeatable results across replications, but also across experiments. Then we're going to set up the call operators, and the call operators are again stored in the instance of experiment. So we again create those as we usually would using the resource class, where the number of operators again is stored within the experiment. We then set up our arrivals generator, passing in the instance of experiment, and run the model as we normally do, and then process results at the end of the run as we normally would. So as an example, let's run a single run of the model. We're going to create a default scenario. Then we're going to call single run, pass in that instance of experiment, obtain the results, and print those results out. So if we run that, we got 3.87 minutes as the waiting time and an operator utilization of 92.9. We run that again, we'll get the same result because we're using a random number set 0 in each run. So now that's set up, it's really simple to implement multiple replications. So that's what this function called multiple replications does. We pass in an instance of an experiment, the results collection period or simulation run length, if you like, and the number of replications that we're going to run, in this case defaulting to 5. So we have a list comprehension within this that does all the work. That's going to create, it's going to run single run, where we pass in the experiment, the replication number, and the results period. And replication number is going to range between 0 and 4, the default case, and we return that and store it in a list called results. We're then going to convert that results into a pandas data frame, which is effectively going to give us a table of replication results for each performance measure. So let's have a look at what that looks like. So here we're creating again an instance of experiment, but now we're going to run multiple replications instead of the single run function. So here we go. This is exactly what we want from a simulation experiment. We have our performance measures across the top, and then for each replication, we've got the mean result. So you can see here that it varies by each result. And if we run that again, we get exactly the same result. So if you wanted to unpack what was going on with sampling in the multiple replications function, we can copy this code, add in a new cell, replace multiple replications with single run, and we can vary the replication number. So for example, if I enter replication 2 and run the code, I obtain from the single run function a mean waiting time of 3.5 and an operator utilization of 94.2. So if I pop back up to my multiple replications table, I can see that's coming from replication 3. If I change the replication value to 4 and rerun the code, I get a mean operator waiting time of 3.1 and an operator utilization of 93.5. And if I scroll up, I can see that's coming from the replication labeled as 5. The difference between 4 and 5 is simply because we're using a 0-based index in our loop. So now that we have an experiment and a multiple replications function, it's dead easy to implement a multiple experiments framework where we batch up maybe 5, 6, 7, 10, 100 experiments and we run them all in one go. So I'm going to give you 3 functions to help you do that. The first is called getExperiments. This is just our example function that's going to create a Python dictionary containing multiple experiments for us to run. We've got the workhorse function run all experiments. That's going to loop through that dictionary and return results for each of those experiments from the multiple replications of them. And then we've got a summary frame function that's just going to make those results into a displayable table so we can understand what's happened in the simulation run. So here's get experiments. It's really simple. We're going to create an instance of a dictionary, and in each of we're going to create 2 entries in there. The first one is the base case, and that's going to have a default experiment. The second is going to increase the number of call operators by 1. So we create an instance of experiment and we pass in the number of operators plus 1, and then we return that dictionary. So the function run all experiments accepts the dictionary containing the experiments we would like to run and the run length. How long would we like to run that experiment for? That's simply going to be a loop. We're going to loop through the experiments. Here there's just a bit of code to loop through a dictionary, and we're going to separate the experiment name from the experiment itself, because that helps us just print out what the name of the experiment is, run the results, and print done. So let's see what that looks like. So if we get our experiments and then we run all experiments, and then let's have a look at the base case. So we can see that what's inside this dictionary are pandas data frames. So for the base case, we've got our 5 replications of the default parameters of the model. And if we wanted to look at the operators plus 1 scenario, we could run that and see what the results were in a pandas data frame as well. So that's nice. We've got 2 sets of simulation results in nice clean tables. Now what would be useful if we could simply compare those, or the mean value of those performance measures in each table. So that's what the final function experiment summary frame does. It accepts a dictionary of experimental results. So the key is the name of the experiment and the value is the pandas data frame containing the replications. So let's take a look at what experiment summary frame returns. So we have a formatted pandas data frame that compares our 2 experiments, base and operators plus 1, across those 2 performance measures that we've collected, the mean waiting time and the operator utilization. So a nice way to summarize the experiments we've completed. So we defined a function called getExperiments where we hard-coded what those experiments would be. But what you could do is actually have all of those experiments defined within a CSV file where each column represents a input parameter to the model and each row represents an experiment. So what I've got here is a bit of code that's going to create an example experiment file for us. It's going to have 2 columns, one that represents the number of operators and one that represents the mean inter-arrival time. It's going to create 4 experiments, the default experiment, an experiment where we increase the number of operators by 1, an experiment where demand is higher than it currently is now, and then a final experiment where we combine both the increase in operators and higher demand. So the rest of the function sets up a pandas data frame that contains that information, and I'm saving it to file. So remember, this is just for illustrative purposes. So if we run that function and create the example, you can then load that back in just to see what it looks like. So this is what our CSV file looks like. So we have a column here for an index. We have an experiment column here, which has the name, and we have the number of operators available and the mean inter-arrival time. To convert that pandas data frame to an experiment is pretty straightforward because of how we set up the experiment class. So I've given you the function createExperiments that accepts the pandas data frame that we've read in from a CSV file. In summary, what that does is it creates Python dictionaries based on the parameters and names of the experiments. It's then going to zip those together and loop through them. And we get a dictionary of parameters here that effectively we pass as keyword arguments to the experiment class. So this allows us to include columns within our CSV file that are named the same as input arguments to our experiment class. And we can either include a few of those parameters or we can include all of those parameters. It's entirely up to you. This code will cope with it and it will update the variables that you've included. So let's take a look at that in action. So what we'll do is we'll read in that example CSV file. We'll call the create experiments function and we'll save the dictionary to the experiments to run. So the key of that dictionary will be the experiment name and the value will be an experiment object with all the correct parameters. So if we run that, we can just have a look at the type returned, which is a dictionary. And then if we print out for the operator plus one scenario, the number of operators from the experiment class, we can see that it's 14. So that's a very quick way to read in lots of experiments from file. You can imagine scaling that up quite quickly to 100 or so experiments that you might need to run in a simulation. So we're back to where we started. We have a dictionary containing experiment objects, so we can pass that to the run all experiments function, return the results, and have a look at the replications. So here we'll just have a look at the first two replications from the base experiment. And there we go, we're back with a replications table. You can look at any of the other experiments as well. For example, if we look at the high demand experiment, we can see the first two replications. So we can pass that again to the experiment summary frame and get a nice, nicely formatted pandas data frame containing a comparison of results. So here we have the experiment as columns and the performance measure as the rows, and we can compare easily across the results to see what is the impact of each of those experiments. If you wanted to transpose this, you could just use the T operator and you would get the experiments as rows and the metrics as columns. In our next video, we'll expand the model to include a proportion of calls that are referred to a nurse for a consultation. Those calls will wait in a queue for a nurse resource to become available, and then that nurse will call them back and there'll be a phone conversation. After that, the call will leave the system. In the meantime, you might want to check out how we originally implemented call triage, and I'll pop that video on the screen here.